this thing? Yeah. That was a good tip to keep it off. I've done that before.
Okay, just take this up and forward. I missed the hair this time. Do a little tilt like that. Cool. And then if you guys just like know who's going to be next, you can just put them on the number 1, and then you guys can turn them on and off yourselves.
Okay.
Cool. Thank you.
Thank you. Hey. Yeah.
Hey, just want to take a minute and thank you for uploading your video. It's been super helpful.
Oh, yeah?
I was trying to find some stuff on XLA about 4 months ago, and I found that you had a few slides in that.
There's like nobody else that's talking on it. Yeah.
And the other problem I found it after I was like to connect deep into it is that you can't run the XLA or compile the XLA stuff on a Mac. And I didn't know that until I just connect deep into it. So
Yeah.
have you tried the Ether yet?
Yeah, I actually have. Okay, so I'll show all this. Yeah.
Oh, so is that something you might be touching on today as well?
Yeah, there's like a notebook and everything you can go on the computer. Yeah.
Brilliant. And the second thing I wanted to ask you, have you tried the Quarkworks factory, the K-Fact?
I have.
Okay. I know you do a lot with pipelines and stuff. I knew compression was important to you, so
yeah, I have.
Thanks, guys. Appreciate it. Once again,
awesome.
Thanks for uploading
Thanks for saying hi. Okay, we got a bunch of speakers. Brett, you're gonna, I think, are you first after my spiel? Which might be a couple minutes, so. Okay, let's get the agenda. Spit out my gun. I'll have to do that later. All right, so what are we talking about today? Oh yeah, so Brett actually gave this talk up in San Francisco a couple, 2 months ago or something? Where did Brett go? Like 2 months ago or something, a month ago? Pretty big hit. We had a bunch of Russians show up. Yeah, actually we have some Russians here tonight. I brought a Go set and everything. We're geeking out before and after. I do want to point out, oh, thank you. That's right. Thanks, Chris. You are here in a momentous occasion because my lifelong dream after leaving Databricks was to get more members on my meetup than the Spark meetup than Databricks. And a buddy of mine actually kind of forgot about it. Yeah, that's not true. I check every day. But when I was at a session earlier today and someone pointed out, they took a screenshot and sent it. So here we are. Well, that's all me. That's not you guys. But yeah, so we actually beat Databricks. They haven't done a community event, like a real community event, in 3 years. So that gave me plenty of time to pick up the pace. Destroyed, went right through Toronto there, left them in the dust. And what else we got here? So let's talk about tonight. So we have Pramit also, who hosted me at datascience.com. He'll be speaking, I think, after Brett. And then we have one more speaker, Andrew, who's going to be talking about more of the business side of things. He had come up to me at 2 or 3 meetups ago, or I think actually the same one that Brett was at, and asked, or said he would be willing to talk about the business side of AI. So that would be a fun talk, something a little bit non-technical. Okay. Well, yeah, it's still going to be fairly technical. So what am I supposed to talk about? Serverless, TensorFlow. Yeah, okay. So a bunch of demos. And then, yeah, also, probably the other thing about Brett, he has a lot of good mobile experience too. So he's gotten, where did he go? Oh, he has TensorFlow working on iOS, and we might partner up and do some kind of morning, get your phone working kind of thing with like TensorFlow. Okay. And then Pramit's going to talk about human in the loop, which is something we like to look at Pipeline too. He's lead like data scientist at datascience.com. Based down in LA, but you guys have a big presence here, right? And you're also speaking, what day are you speaking? Speaking Thursday? What time? That's the exact same time as me. So. Yeah, he also has this cool framework called Skater, which you should check out on GitHub. He's been pushing that recently. He's a big fan. Let's see how many. Ooh, that's a broken link. Oh, there's a comma in there. Is that? Oh, that's on the Meetup. Okay, I can fix that. That's my fault. And this has, yeah, the elements of the human in the loop. Okay, so you'll talk more about that. I do want to highlight a couple cool things, like a lazy ass sitting down. If you guys go to the community edition, we have added a bunch of cool things. We picked up a project called OpenFaaS. There's a guy out of London that has been pumping that thing. And it's a pretty cool project. So you can basically functionalize anything that you can script. So we kind of pull that in for some ensembling and some like ad hoc kind of stuff. So actually, let me just start here at community. This is like a fun little demo here, so you can draw, and I think this works on your phone too. So I spent like a day trying to get it to work on the phone. Ooh, that wasn't a very good prediction. And what's fun is that you can like predict. This is a feature that I haven't yet finished, but we have another guy coming on in a couple weeks who is going to backfill me on the engineering side of Pipeline, and then I'm going to go forward with whatever else a business requires at that point. And you can actually, we can shift traffic here live. I have the controls exposed there. Yeah, so we've added some cool features to this. This is, this is going to become like a full-fledged demo here at some point. And this we also picked up here. This is kind of cool. You can grab and actually do curl commands right, from your shell. It makes it nice and easy. This is a little trick I picked up from another co-opetition that had this and was kind of nice. I just built TensorFlow from source. So the version of TensorFlow that you get in Jupyter here is usually about like 2 or 3 days out of date. What's cool about this build too, so this is probably closer to TensorFlow 1.7 than it is to 1.6. I have Kafka turned on here. So you can actually, from the same dataset API that TensorFlow exposes, you can pull in data from like Kafka as well. So it's using the C like Kafka like libraries beneath the covers and hooks into the dataset API on top. So that's actually where this is going to lead. When we go to correct this prediction, that's going to end up in a Kafka queue or topic and then get pulled, and then it's going to be retrained and new models will be pushed out. Also, I've got one other kind of fun feature. I've talked about it like many times. We've implemented it before, but I'm pulling it into community where you can actually, when you do correct it, or when we detect sort of borderline like confidences here, if there's 10 options and they're all about 10%, we'll actually put that onto a Kafka topic and post it to Slack, which is cool. And then Slack users within the company or outside can actually correct the predictions right from Slack. So Slack is like becoming kind of a like application development environment, which is kind of cool. It's got a nice clean API and all that stuff. So the cool thing here is you can hit predict like 1,000,000 times. And let me refresh this. You should see 2 versions of the model. Predict. And so it looks like someone might have shifted the traffic. We could also do shadow the traffic. So we're going to shadow to B. That makes a REST call in the back end. And if no one else touches it, we should be able to. What's cool is we could see that this is actually coming back from variant A, but B is still getting traffic. So it's A, and then we look and we see B is actually taking traffic. So that's our shadow mode. So that's kind of cool. These are actually the exact same model, so they're going to have similar performance. But you can split between A and B. What else here? The function stuff. Oh, yeah, and if you're curious, you can go look at the Kubernetes cluster, and Etro and Will. What else we got here? Here's the OpenFaaS stuff that we're looking at, like integrating. We basically have a lot of these features. It's just, this is a pretty cool project. We wanted to pull it in and see how it matches. But you can deploy a new function, and they have this concept of a store kind of thing. You can grab somebody else's Docker image and then deploy it. Or you can specify your own coordinates, and then like we would actually extend this even further, where you can like copy and paste snippets of code right in there, and like like requirements TXT and that kind of stuff. So instead of building this separate UI, we're actually going the route of actually integrating into JupyterLab itself. We like JupyterLab, and the idea here is that you would right-click on the model. This is one I was working on last night. And you would then deploy it. So, all right. Also, by popular demand, we have Airflow back in here. One thing that the new guy is going to work on is like a clear S3 story, right? Like a clear, yes, all these things will point to the, so you can configure it to whichever buckets you want. So something I dealt with all the time at Databricks. Some of you might notice 2.3 just came out, I think 2 days ago. This runs on top of Kubernetes, so we pulled that in. I was up all night the other night getting this working. And you could do even, there's a new command now in the pipeline CLI, spark cube scale, replicas equals 5. And within seconds, let's see how many workers are there, 2. We have 4, and then we have 5. Boom. So nice way. One thing that we've learned from Databricks, and then since then, actually Databricks doesn't really do this, but there's like more and more people that are creating one cluster per job. And back in the day, creating one cluster per job seemed kind of wasteful. And this is before containers and before these nice orchestrators that are here. So at Netflix, this is what we did. So for Databricks, I was at Netflix, and we would actually cobble together what version of Spark that you wanted, which version of Hive, blah, 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 pull it down, and basically each person could then operate. And that whole job, it was super easy to like debug and like reason through the resources, because you actually spun up all the EC2 instances. It was all done behind the scenes, of course. So a little bit easier now to do this. So that's one principle that we're pushing through. And what else? First, we've got TensorBoard here. Haven't trained a job since I restarted, but and then there's a quick start if you guys do want to get pipeline going. I want to point that out. I don't know if I've highlighted this much before, but we do support SageMaker. So SageMaker hit the scene. This is Amazon's way to take Docker images and then deploy them specific to machine learning. You can do training. They actually support distributed training as much, if not better, than Google, like distributed TensorFlow training, which is kind of interesting. So our API or our command line and like REST API support SageMaker also, so you can run it on Kubernetes and run it on SageMaker as well. Okay, and so yeah, you can follow these. Docker also now, if you have updated to the Edge or to the latest Docker Edge anyway, has Kubernetes built in, so you'll actually see a little Kubernetes cluster down here. And so that's kind of nice. You can, so before this, and this just hit the scene about a month or maybe 2 or 3 months ago now, we had to actually bundle everything into one Docker image for the development side of things. And then we have a different setup for the cluster, but now we can actually run the same thing locally. So, all right, that's an update on my side. Did you get the link? It's the same as that last one, 773-456-3443. All right, is Andrew here? Andrew's stuck in traffic. He's the last one. So, okay. Any questions? I'm not going to have time, and I don't have the TPUs running. But any questions about my talk? Anything you wanted to know specifically? No. Yeah, that's a good question. Usually between 8 and 10 hours. So yeah, that's one of those things. I go to bed, I wake up at 3 in the morning to make sure it's still going, and then I have to do whatever to restart it. Also, TensorFlow serving, we have that building pretty cleanly, but there's a whole ton of optimizations you can turn on. There's like the MKL for like Intel. I actually have the TensorRT stuff built here as well too. So that's kind of the next step of like optimizations for the GPU. You could take the same TensorFlow model and then generate this TensorRT binary that can run inside of those pipeline containers. Also, GTC is coming up, the GPU Tech Conference. It's probably the best conference outside of O'Reilly's Strata conference. That's a really good one. It's like $9,000 per person or something, but it's like totally worth it. And I'm speaking, so for me, it's $9,000 that I made. All right, are you up? Did you get the dongle? Yeah, because they actually produced a bunch of them. Apparently, they're not as scarce for resources, I thought.
Super confused 2 hours ago.
That's awesome. All right. This is the video. And then this is the microphone. Playing a different microphone situation. Yeah.
This one, can you move your laptop?
Yep. It's your I've seen you before. Oh, God. Yeah, I've talked to you before. Oh, really? No.
Oh, have you been working with
Yeah. Yeah. If you go through the quick start, there's the census model that I have. Yeah, it's okay. It gets a little flaky here. Yeah. No, I definitely not happy, but you can take care of work, like occasionally. You throw it on over there. Cool. I have to plug in too because I'm recording. You should just, are we on the same meeting? Yeah.
I joined your meeting.
So you do screen share. Yeah, don't do the video. And do unmute. And do screen share. Yeah. Okay. Oh. Okay. Yeah.
I'd like to thank you all for showing up. I put my slides online if you want. I put my slides online if you click along and look at what we're doing. Okay, good. I'd like to thank Chris for loaning his soapbox, so to speak, and for all of you all not being out drinking at vendor-sponsored parties right now. So, quick show of hands. Who here works with TensorFlow in that capacity? Okay. And who here is neural networks? And then who here has played Go? Okay. My background, I used to play a lot of chess. And a few years ago, I went back to grad school to get a master's in science. I took some AI courses. And Professor Yisham let me write cobots for a couple of semesters. This is all this AlphaGo stuff happened. So I've just been sort of watching it from afar and just studying it. And so I did this presentation just to put all my thoughts together. So here we go. We'll do like a super brief overview of Go, discussion of the rules of the game. We'll look at how you can combine an algorithm called UCT with random rollouts to produce Monte Carlo tree search, which is the basis of all the modern approaches to this game. From there, we'll look at how the Google team combined Monte Carlo tree search with policy and value networks to produce the AlphaGo series of engines. And then last year, they combined the policy and value portions of this engine with self-play to produce AlphaGo Zero, which came out like last May or so. And then in December of last year, they released AlphaZero, which is like a AlphaGo Zero, but without the Go or Go-specific knowledge. So it's like a general board playing algorithm that you can apply to other domains. And then we'll do like a very quick demo of that at the end. If you've never seen a Go board, here's what it looks like. The basic objective is to sort of fill the squares of the board with stones, capture as many squares, while your opponent's trying to do the same thing. Go comes to us from Asia. There's arguments about where precisely it was started, about 2,500 years ago. There's arguments about when it was exactly invented. The Go at a master level is played on a 19 by 19 board, which gives you about 361 squares. There's a few different scoring systems in Go. The one we'll focus on is the Chinese scoring system, which can be summed up as being nothing more than the number of squares that you own, or the number of squares that you have stones on at the end of the game, plus the number of stones that you've captured. The first player to move in Go has a little bit of advantage. It's black as well, not white, if you're used to chess. And so at the end of the game, black loses or has 7.5 points subtracted from their score in order to balance things out. A half point means that there's no draw in Go. So one side or the other always wins. The game will last about 300 moves. This gives us a state space about 1 times 10 to the 170th power. To try and put that in perspective, chess is about 1 times 10 to the 50th. The number of atoms in the observable universe is about 1 times 10 to the 80th. So if you can imagine a universe for every atom in our universe, you're still slightly shy of the state space of Go. Because of this, Go has historically been it's been like the holy grail of AI research. It's always been felt to be out of reach. About a decade ago, some new algorithms appeared that we're able to finally take it off. The first part of the algorithm is called UCB, which is something that comes from us from probability math theory. It's called the multi-arm planning problem, which is a fancy way of saying how do you win the most money from rolling slot machines given a certain number of quarters. The basic idea of the UCB algorithm is to explore new machines. You want to put all your quarters into one machine, and then find what you think is a winning machine and then attempt to maximize your winnings. UCB actually doesn't actually give you the best algorithm for making money from machines. It's actually sort of designed to give you the least worst solution. But whenever you convert the least worst solution from that domain into game theory, the least worst move is the best move, basically. The next improvement to UCB was to combine it with trees. So at the bottom here, we have basically what UCT algorithm would look like whenever applied to a Go board. So we start off with a game tree. We decide that we want to evaluate a new move. We evaluate our move. And then we say, for example, in this picture, we think that black's going to win the game. So we go back to the tree. So black would want to go towards this line, so we increase their score and their probability of winning. But then we go up a move, and white would not want to go down this line of play. So they would decrease the odds of them playing this branch. You go back and forth until you get finally to the top, and you repeat your whole cycle over and over again. The UCB algorithm itself is pretty, it's a valid way to approach this game. But the C step here, the evaluation, is where the real magic happens. Because unlike the slot machine, where if you put a quarter in, you can instantly find out whether or not you win. With Go, it might be 200 moves until you win the game. So historically, they did not have a good heuristic. About a decade ago, they came up with random rollouts. The basic idea is to take the current board state and simply add stones to the board randomly until both sides cannot play, so they pass. And then you can score the board using the Chinese rule set, which is easy to implement. And then just very simply on who has the highest score, that gives you your win or loss prediction, and then you can go back and update your tree. So this combination of UCT with random rollouts is called Monte Carlo tree search. And this can be proven to asymptotically approach perfect play on a Go board. The only minor bug is that this will take longer than the universe will ever exist. But that's what mathematicians call an implementation problem. So a couple of years ago, as you're probably well aware, AlphaGo appeared out of nowhere to become the world champion in this game. This is the former world champion of Go, human player, named Siegel, realizing he's probably going to be one of the last people that ever beat a game over the board. There's about three different AlphaGo engines in the papers, if you read them. The original one is AlphaGo Fan. This is about 2015. Fan, he was like one of the strongest players in Europe, and they did a demonstration match against him. Then there was the AlphaGo Lee engine from 2 years ago. And then finally, in January or so of last year, Google released a paper with the AlphaGo Master. But these three engines are basically roughly have a similar basic algorithm. So we're going to go through that right now. The basic idea of how these engines approach the game is to take the Monte Carlo tree search approach, but to improve your search algorithm. So first, we use a policy network to quickly make moves. We want to test fast moves that are good rather than maybe random ones. Secondly, we want to use a value network to predict the winning odds of a particular move. So rather than performing a full rollout or simulation, if we can just get a good guess for whether or not we think a particular line of play is going to win, we can explore more area of the tree. And then finally, we don't get rid of the Monte Carlo tree search at all, altogether, rather. We still use it to perform deeper evaluations whenever we need. So we're still building upon this solid base. So now so how do we build this? The policy network is probably the closest to traditional machine learning, if you will. They took a collection of human games, about 150,000 of them, and applied supervised learning with a CNN to basically construct what they called a policy network. So given a particular position, can it predict the next move? Then they took this policy network and recombined it with the Monte Carlo tree search to play a lot more games. So now they had a larger collection of both human and computer games, and then they could rebuild their policy network again to produce an even larger, stronger network, which is the reinforcement learning part of this process. The end goal of all this is to use the policy network to make moves rapidly. So the first engine they constructed was able to make a human-looking position move in a particular position about 55% of the time, which was significantly better than the other attempts to do this at that point in time. But moreover, it can make that prediction in about 3 milliseconds. They then constructed the second version of this policy network that wasn't even really a neural network anymore. It was based on like a softmax function combined with like small 3x3 patterns. So this one was only like half as accurate, we'll say 24% as accurate. But this smaller engine could run even faster, and so it can make its predictions in about 2 microseconds. An important note that we'll come back to here in a second is that this policy network alone, which is just sort of copying what it thinks a human would do in a particular position, doesn't actually have any true knowledge, we'll say, can actually beat a number of engines. The second part of the equation is to build a value network. The basic question we're trying to ask is, from a given input state, can we predict who's going to win in a particular situation without actually having to perform a full simulation? So for this, they constructed a second CNN, similar to the policy network one, to simply predict the winning probability given the input position. They trained it on the MSE between the prediction and the outcome, and then they had a second heuristic of how many moves it was to the end of the game. The problem with this approach is basically that the network just copies its input. It overtrains to its input gains. So they had to relax the network. If you look at a Go board, you can imagine that you can turn it 90 degrees. You know, the moves, the stones would all have different numbers for where they are, but the game itself would remain the same. You can take a board, you can rotate it 4 times, and by the same idea, you can also take the board and flip it over itself. So each game can have 8 degrees of freedom. So by taking the original games, adding this 8 degrees of freedom, it allowed the network to properly train. And then ultimately, like the policy network, we use this value network to make quick predictions. So it can run about 15,000 times faster than an actual Monte Carlo tree search simulation. So on this slide, we see the power of combining these different approaches. Starting on this side, we have the 2 versions of AlphaGo. This is AlphaGo Fan. And then the third one is actual Fan Hui, who's a human player, who's like about the strongest human player in Europe, one of the strongest human players in Europe at that point in time. These red bars are like 5 contemporary Monte Carlo tree search based engines of that day. And then on the far side, we have the AlphaGo components. We'll start on the very far right. So the very farthest right is just the pure Monte Carlo tree search part of the AlphaGo engine. What's interesting to me about this is that it's actually weaker than the other Monte Carlo tree search engines of its day. The next one over we have is the policy network. So this is just simply a neural network that's emulating human games. It's actually even slightly stronger. Next, we have the value network, which is just a network that can very quickly evaluate moves. I would argue it's weaker at playing Go, but it can do a lot more simulations, so it can explore more of the state space, so it's stronger by that virtue. As we keep on coming over, though, we can see the power of combining these different approaches. By combining the Monte Carlo tree search with the value network, we can get about a 500-point improvement in performance. By combining the value and policy networks, we can get a little bit more. And then finally, by combining Monte Carlo tree search with a policy network, we can get almost up to 2,500 ELO rating. And then finally, on this bar graph right here, we have the all three approaches combined together. So we have the Monte Carlo tree search, value, and policy networks. And that was produced the full-blown engine of AlphaGo that was able to beat FanHui in their demonstration match. The interesting one to me from this slide is the third one going that way for the AlphaGo engines. This is just the pure combination of value and policy networks with no Monte Carlo tree search. The reason this is interesting to me is because it's the basis of the AlphaGo Zero engine, which came out last year. AlphaGo Zero built upon this foundation, but it had a couple of important concepts. But the largest one, I would say, is basically that we input a position, we use a single network that combines both the policy and the value networks together to predict simultaneously both the best move and the winning odds of that move, which we can then use to build our game tree. Because we're using one network then, we can play games against itself, we can train a new network to categorize wins and losses and reduce the prediction error, and then finally, we can evaluate the new network against the old one and pick a winner. And from there, we repeat this process about 700,000 generations, and we have master level play, starting from a completely randomly initialized state. So now we'll go into how the actual neural network in AlphaGo Zero works. This is a cheat sheet you can get off the internet, which is a nice PDF, and you can zoom way in and see everything in great detail. We'll go through the first three parts here a little bit more deeply here in a second. But the basic concept is that we play games against ourselves. We train the neural network against that. Then we play the new neural network against the old one, pick a winner, and then repeat the process. The far slide we have over here is how game state is actually encoded for the AlphaGo Zero engine. It's 19 by 19, a full board. So we have eight stacks for black, the last 8 moves for black. We have 8 stacks for white, the last 8 moves for white. And then finally, the last layer is simply black or white, depending on who is going to move. And so this is how we store a single state for the AlphaGo engine. And then we come over here. We take our input state and come over to the bottom left corner. We apply a 3x3 convolution, a batch normalization, and a ReLU step. And then from there, we go over here to the far right side, bottom right. We do another 3x3 convolution, batch norm, ReLU, 3x3 normalization, 3x3 convolution, batch norm, and then we add a skip connection. This network uses a ResNet style approach. And from there, we simply have 40 of these blocks going all the way up. And at the top, we have on our left a head to output the whether or not we think a move is our winning probability. So we have a value head, and we have another node on the other side that outputs what we think is the best, the most likely move in this position. So the policy. So we take our input state, run it through 40 residual blocks, and at the end we have either a prediction. We have both a prediction of what we think the best next move is, and a score for how likely we think that move is to win. From there, basically, we can take our whole network and flip it away upside back down, and basically we can reconstruct our Monte Carlo tree search style tree, but here, now we can just use our single neural network to do all the steps. And then finally, we apply like a global simulated annealing style temperature schedule just to make sure we don't get stuck in a local minima or maxima while we're beginning our state space search. This is they tried a few different network architectures. This is what they ended up with. I didn't do this, by the way. Oh, sorry. So here we can see how this process plays out as we're actually training things. The network starts out extremely weak. It basically makes completely random moves. It takes it literally a day or two to reach the player, like almost even just beginner level play. But then it slowly improves until it passes. The dotted green line here is the AlphaGo Lee that played against Lee Sedol. The top one is the AlphaGo Master engine, which we'll talk a little bit more about here. But finally, it just surpasses all these other engines and just ends up in its own, world of, it's beyond anything that's ever been done before and has nobody to compete with anymore. This other graph here is basically the 2017 version of our ELO ratings from before. So we have our same Monte Carlo tree search style engines over here, the red blocks. And then coming this way, the far dark blue one is the AlphaGo fan engine from before. The next one is the AlphaGo Lee engine, which is a little bit stronger still. And then you have the AlphaGo Master, and then a little bit higher up there is AlphaGo Zero. A portion of the reason that they were able to make these improvements between these engines had to do with just simply increases in computational power. The AlphaGo fan was trained on about 172 GPUs, similar to what probably many of you have. AlphaGo Lee was trained on a cluster of 48 TPU1 devices that Google had. It's their own internal hardware. And then the AlphaGo Master and AlphaGo Zero were trained on a cluster of 4 TPU2s. Sorry. So we'll go a little bit into the differences between the AlphaGo and Zero and AlphaGo Master. They're both trained on the same hardware, but the second engine is able to achieve a little bit higher performance. But the one thing I would like you to remember is this raw policy network from the AlphaGo Zero engine, which is the gray bar here, which is able to play at about 3,000 level rating. We'll come back to that one here in a second. The difference between the AlphaGo Master and the AlphaGo Zero approaches comes down to a couple of different things. This bottom slide is illustrating the differences between two important tricks. One is that the AlphaGo Zero uses ResNets as opposed to CNNs, so it can be trained to a slightly lower amount of error. And the second thing then is the combining both the value and policy networks. So the Google team actually built a version of the engine that trained a policy network on its own and a value network on its own and combined the results at the end. But as you can see in this bottom left graph, combining the two things together to have a shared goal state, so to speak, I think gives it a solid like 500 to 1,000 point increase in performance, just because it can actually, they're not the two things don't have separate goals, we'll say. And then the second part is that the ResNets allow you to train to a higher degree of error. So the top left right here is basically showing you the difference between the supervised learning and the reinforcement learning approach. So the supervised learning actually does pretty well. It starts out very quickly. It learns from the games it's shown, but ultimately it cannot improve beyond its input data set, so to speak. It becomes limited by its data that it's trained on. The reinforcement learning starts out much slower, takes a lot longer to improve, but because it doesn't have any limitations upon its growth, it's able ultimately to achieve that higher level performance. Okay. So this slide is showing you the AlphaGo Zero training as it's part of the process. So we start off over here from 0. As we go across, we're getting deeper and deeper into training. So from 0 to 72 hours is about the amount of time it goes from being a raw beginner to playing at a high expert level, we'll say. So at the very beginning, if we go down here to this bottom left slide, you can see that the engine is just trying to gobble as many stones as it can. It's playing like a pure beginner. It's just playing purely for stones. If we go a little bit further into the game training state, though, it's starting to branch out and play on the edges of the board. And then finally over here, it finally has, like, we'll say, a full board vision and a global understanding of the game. If you play Go, for example, if you're familiar with ladders in Go, the engine actually doesn't learn ladders until very late in its training, which is something that's interesting, I think, because only after it's learned all the little bitty parts of the game can it actually have the global vision to see that it can't move its stones across the board like that. Ladders are like a play that's off the top of the beginners. It's an easy pattern for them to learn, but this engine doesn't learn that until after it's basically mastered everything else. If we go across the top, we have various Joseki. These are basically opening patterns in Go. What's cool about this is that the engine, starting off from completely blank, randomly initialized state, as it improves, basically rediscovers 2,000 years worth of opening theory in this game and learns how to apply it and learns how to refute it as well. So if we take these top 5 Joseki, we can see right here a graph, the same axis of time played, and then the second axis for up and down here is how often it's actually playing it. So it discovers some of these openings, plays them a whole bunch, discovers how to refute the opening, and then abandons it altogether, so to speak, like this one right here. And in other ones, it discovers and decides that it loves them and keeps on playing them a whole bunch. But yeah, so basically, this combination of these approaches is the AlphaGo Zero engine, and it more or less is solved the game of Go from a practical standpoint. No human player will ever be able to beat a computer again. I'm sorry, and that's the current state of affairs. So from here, we'll go into AlphaZero. This is a paper Google released in December of last year. And it's a generalized version of the AlphaGo approach, but it doesn't actually have any Go-specific knowledge. All the AlphaZero algorithm takes as input, it takes a board state, a list of possible moves, an evaluation function in some form, and then from there it can generate value and policy networks by playing against itself. So you can give it these 3 input conditions. It can teach itself how to play, and it'll quickly improve to master level given enough CPU time. So they gave it a chessboard. They trained it up. It plays chess at like a 3,000 level, which is the grandmaster level. They gave it Go again, and it taught itself to play Go. It should be noted that the AlphaGo Zero, the green line right here at the top, is like a version of the AlphaGo Zero engine that was only trained for 3 days. The full-blown one that was trained for 40 days is significantly stronger, so this one can't actually beat AlphaGo Zero. The middle one is the one that's cool to me. Shogi is a game from Japan. It's similar to chess, we'll say. It's played on a 10 by 10 board. Historically, it's not been well studied. It's not been one of the cool games, so to speak, but they were basically able to give it the input board state list of moves. It was able to produce a master level player without, just by adding CPU time. All right. Okay, one more. So here we can see AlphaZero, similar to the Joseki of Go. Here's AlphaZero teaching itself to play various chess openings, and then either embracing the chess opening and using it a whole bunch, or learning it and then deciding it wasn't really that great of an opening and abandoning it. So what's interesting to me about this is that I play a lot of chess. I play the English opening. I like the English opening. A lot of players for black play the Sicilian defense. It's kind of popular because it's an aggressive, dynamic way to play, but the computer does not like that opening at all. One of the arguments against the Sicilian defense is that it's the English opening, but with one less move on the board. And, that's, and so what's interesting is AlphaGo likes like a number of openings that were popular in the 1800s, but fell out of favor because they were felt to be, not, aggressive enough. All right. So now we'll apply the AlphaZero engine to a slightly smaller problem of tic-tac-toe. If you're not familiar with tic-tac-toe, you have a board, you have 3 rows, you fill out X's and O's, and then, yes, if you play perfectly, you should always be able to draw. But it's a board game, just like these other ones, and we can model it the same way. So we have a 3x3 board. In tic-tac-toe, any empty square is a legal move. And then our evaluation function is if there's 3 in a row, that's a win. So we'll set this up. We'll play a basic loop. It'll play games against itself. We'll train a network using Keras and TensorFlow to recognize the winners and minimize the losses. We'll evaluate the new network, and then we'll repeat the process until we have a tic-tac-toe bot. This is what we did wrong last time. We didn't share the other screen, so.
Oh.
Yeah. Okay, this is okay. Okay, so deep blood hole. All right. Okay, this is some code I got off the internet. A student in Stanford named Serge Nair wrote a AlphaZero implementation in Python to play Othello. And then a Russian guy by the name of Yevgeny Tyurin modified it to run tic-tac-toe. And so I'm just running his code. We'll run the script here. Okay, so it's going to play about 50 games of itself. Sorry, it'll run about 50 games of itself. Then we're going to train the network using Keras and TensorFlow. I modified his code slightly. He runs it for 10 epochs. Mine only runs for 3, which can be a little bit dangerous because it doesn't always play perfectly, but hopefully this will work.
So Brett, while this is running, you had shown the state space to be about 8 white moves, 8 black moves, and current probability. But on your earlier slide, you said it had almost 10 raised to the power of 170 moves.
Sorry, that would be the state space for a single move. And then, sorry, that's how the state space is encoded for the network itself. I'm talking about, like, you know, there's 361 squares, there's 3 possible states for each square, and 300 possible moves. That's how you get to that other number. Okay. So we've trained the network. Now we play the new network against the old one.
Are you running this locally or somewhere?
It's on my laptop, yeah. I could have gotten a cooler cloud one. Okay, so our random model actually beat our attempt of training a first model. If we let this run deep enough, though, it'll converge to a proper engine. But we'll stop it right here because this is going to start taking a while. I have here's the safe state of our neural network. And so we'll play it against a properly trained network that had about an hour worth of CPU time. And we'll see how well our little bit bot that we just trained does. So now they're just blindly playing against each other as fast as possible. We'll have them do 100 games. Okay, so our new engine, I'm playing against a perfect engine, won 0 games, lost 46, but managed to draw 54. But if we sit here and let it run for an hour, it'll play perfectly, and there'll be 100 draws if we let these two bots play against each other. Okay. What's cool about this then, though, is we can open up our board state space right here, and his implementation of tic-tac-toe has 3 squares. So if we take it and change 3 to 4, now we can have 4 squares. And now we can go back here and we can rerun our training script. Okay, so now each game will take longer to simulate. We'll have to play more games, and we'll have to train for much deeper, but if we let this one run, it'll take about, we'll say 20 hours to 24 hours, a day almost. We'll have an engine that can play 4x4 tic-tac-toe perfectly, so on and so forth. So we won't watch it here.
Now, Clint, have you explored any transfer learning tricks where maybe learning one game could help you get a running start with another game?
This can be, we for the AlphaZero engines, we start from a random state, so we don't actually have to do transfer learning. So here is the 4x4 version of tic-tac-toe. Do you guys want to try to play against the bot? No? Okay. 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 All right. Okay, so a recap of what we've seen so far. We've seen how Monte Carlo tree search in the form of UCT plus rollouts solves Go, so to speak. That approach doesn't really scale. We've seen how you combine expert knowledge in the form of prior games with value and policy networks, which can be thought of as being an optimization on top in order to surpass human players. From there, we've seen how a single network, randomly initialized, can reach even greater performance via self-play. And then finally, I would argue that this approach generalizes to other domains and is very human-like. So what do I mean by that? Well, I will ask you the question, what is AI? We'll start off with what would be like the Chinese room example, which would be like, we'll say, the negative case. You might say to me, I can play tic-tac-toe perfectly. I can play tic-tac-toe perfectly all day long. And I say, great, show me. Let's get a piece of paper. And we just start writing down all the possible games until we've enumerated every single possible tic-tac-toe game on a 3x3 board that's possible. And I can take this stack of papers and give it to somebody else who doesn't even know how to play tic-tac-toe at all. And I can say, just find the position that's in the book, and make the next move. We could do this for 3x3 tic-tac-toe. We could do it again for 4x4 tic-tac-toe. It would just take a bigger book. If we were to take the AlphaGo 0 policy network and we could somehow print it out, it would be incomprehensibly large, but we could somehow print it out. We could make a gigantic book that we could hand to any person in this room, and you could play Go simply by taking the book, and whenever your opponent made a move, opening it up to the right page and making the next move. And because the AlphaGo policy engine plays at about like a 3,000 level, you would be like close to world master status without even having to understand what you were doing. So then, based on this, all we've really done is invented like a fancy form of compression, we'll say, a way to compress the state space down. This would be like what I would say to be the negative example. So let's go the other direction. If we were to teach somebody these board games, what would we do? We give them a board, we teach them the rules, and we have them do practice. And really, that's all we do with this engine, right? We give them a board and the rules, and we have them do lots and lots of CPU time, but it doesn't really have any advantage that we don't have. Moreover, the question then becomes, what is the difference between a master level player and a beginner? I would argue it's not that the master necessarily can, like, say, mate in 36 or whatever, and knows everything to do in any situation. It's more that the master level player sort of knows what situations to seek out, what situations to avoid. And the reason they can do that is just because they have lots and lots of experience. So about 100 years ago, there was a world grandmaster of chess named Jose Casablanca. And they asked him, Casablanca, how many moves ahead do you think? And he said, I only think I had one move, but it's the right one. And at the risk of anthropomorphizing our Go bot, if you could ask AlphaGo Zero that question, it would tell you that answer is absolutely correct. Okay, yeah. If you're interested more in this subject, read these 4 papers by David Silver, and that's all you need to know. Okay, thank you for your time.
This is pretty. datascience.com. Yeah, awesome. So this one would be like 30 Share, you got that on, okay. I'm recording. Cool. Okay.
Few minutes old.
Cool. Hi, everyone. Thanks for making time so late in the evening. So let's get started with the topic right away. So I'm here because, predictions often go wrong. And this is a good example. The robot is trying to pick something up and then messes up and then just falls. So I'm a lead data scientist at datascience.com. Off late, I have been exploring better ways to extract, evaluate, and explain models learned decision policies. Before that, I used to work for eHarmony. I used to do matchmaking, delivering love, or finding the best possible match. I'm also a principal author of Scalar, the open source project that I'll be talking about. And if you guys happen to find yourself in LA, I also co-organize PyData SoCal Meetup. So feel free to leave a message. And we'll be happy to host you guys if you guys have an interesting topic to talk about. So today's agenda is to talk about the problem of opacity. We're going to define what I mean by model interpretation and why it is needed. We're going to also talk about the scope. We're going to understand how we can enable interpretability. We're going to specifically talk about a particular algorithm called Bayesian rule list. And when we talk about interpretability, there's often a tension between interpretability and performance. And performance could be multifold. It could be model's scoring metric, or it could be computational resource and so on. We'll look at some benchmark numbers. I'll tell you guys more about Scalar and how you guys can use, get started to build VR models right away, and future work and literature references. So now that I've laid out the agenda, when I say model interpretation, how many of you guys here have an idea of what I mean by that? Or, let's keep this session interactive. So what does that mean to you guys? Yeah, I mean.
What is the stable space or which the model?
Yeah, that's possibly that we could define one way. Any other take? Cool. So let's make sure that we are on the common page with respect to the problem of opacity, right? We're talking about AlphaGo, reinforcement learning, bandit algorithms. And so the thing is that we have a lot of sophisticated machine learning algorithms out there. And everybody is building the most complex model ever. But there's a big problem. And Gartner has summarized this pretty effectively. There's a lot of ethics violation which is occurring as we are building these models because of a lot of biases which are there in the data on which we're training these models. So, we get the training set, we get the sample set, we split it into train and test, and we create this black box model. We create a predictor, which is a scoring function, and we hit the data set to that, and we get some output. All that is good. If you go on Google and just search for churn model or something, you'll get enough code snippets that you can copy and paste, stitch things together. And most likely it may so happen that on your test or validation scoring set, you might land up getting a 90% accuracy. You go and deploy that model and you'll land up that, and you'll realize that it's not even doing better than a random guess. And that's typically the case. And that's the reality. Often enterprises have been spending millions and millions of dollars on, I was about to say on the name of AI, but in the name of AI, but with respect to machine learning as well. And they realized towards the end of it that we're not doing, the results are not moving the ROI metric. They're not giving the profit margin. So, and I've gone through this exercise many times myself. And the key factor is that data science, machine learning, predictive models, more often than not, if it's not a research-oriented project, is very closely tied to the business. And it's very important to understand what is that the business is desiring. So with that, let me define what do we mean by model interpretation. So as I can get your name? Pushkar. As Pushkar mentioned, it's maybe some an equilibrium state where the model is performing equally well. That is good. So we know that there are like a lot of model metrics, defined model metrics for different types of machine learning problems. Say if it's a supervised classification problem, we know we can compute some AUC ROC metric. Does that name or metric means, does everybody know about that metric, right? Right. Or, you can, let's keep it more simplistic, say accuracy. We could just compute how many times the target label predicted something, and the target had a goal label that was 1, and we predicted 1 equally well as a number of use cases that was there. But we are defining model interpretation as human understandable aspect of model evaluation. Now, when I mention human understandable, it means that the output should be self-descriptive. That is, even if it's an executive, a person who has no statistical or machine learning background, he looks at a model or looks at an output, and he knows what he's looking at. At the end of the day, that's the business use case that we're trying to solve. Churn, whether the customer is going to churn or not. If the person doesn't churn, what are the key features that actually contributed to that person not churning? Fraud detection. This person was so-and-so was denied a credit card. What were the reasons for that? Was there a bias which was committed by the model, or was there a bias in the data itself? Now, as you can see, these are very human interpretable questions that we are asking, and it would be great if the results are also in that form, or there is a way where we can hit the model and ask these questions. So now that we have defined model interpretation as interpreting model in a human understandable way, what do we want to achieve with it? With model interpretation, we want to answer the following questions. Why did the model behave a certain way? What are the relevant variables that is driving a model's outcome? As I was talking about some of the use cases. What other information can a model provide to avoid false positives? How can we trust the prediction of this black box? Is the predictive model biased, or is my data set biased? Remember that in this digital age, we are exponentially collecting a lot of data. But as we do that, we as humans have a lot of bias ourselves. And based on those biases, we act a decision. So those biases are actually getting introduced in the machine learning models as well. So stating that, let's make sure that we are on the same page with respect to a typical analytical workflow. So we get the data, we define some hypothesis. We identify the key features, we do some feature handling missing data, and so on. And then we move on to engineering and selecting the most appropriate features. And then we go on to build this model. We build a black box model, or maybe say a Bayesian model, and then we operationalize it. Now, why I've highlighted it as this build model and deploy model as green boxes, because not all the models actually get operationalized. You may be surprised as to the number of experiments a data scientist actually makes and the model that actually gets deployed in production. There's a big gap in experimentation and reality, and that's causing a lot of chaos in the industry. So the idea with model interpretation is, how can we close this gap? You're doing an experiment, you want to deploy a model. Cool. Can you explain the model in a way that everybody could understand? Is there a way we can debug and understand why a particular false positive is occurring? When the model is operationalized, can we again do that in a consistent way? Now, in this approach, like Chris was mentioning about his example on model testing, that's one way to go about it, but there is still more to be done. So as I was mentioning, why model interpretation? So let's, are you guys familiar with the producer-consumer paradigm? Right, so initially I had a lot of engineering background. So if you're looking at a buffer, you have a producer which is continuously producing, and you have a consumer. Now, if the buffer size is not big, then there's going to be a lot of a conflict, the productivity would go down. And it's kind of the same. So let's imagine that the producer in this case is the data scientist who is actually building the model, and the consumer is the decision maker. It's a typical problem in the industrial setup. And this consumer could be a business owner, could be a human who is being affected by the model. Once the data scientist has built a model, is giving 99% accurate results on validation set, the person he or she is very happy, goes to the business decision maker, and the business owner asks, explain the model. You'll be surprised how often the idea gets crushed just at that point in time, because maybe there is a bit of communication gap, maybe there's a knowledge gap. But as we're building these complex models, it becomes very difficult to explain or articulate in a human interpretable way. And that is a big problem. And primarily a reason why a lot of the ideas with respect to the sophisticated model don't get deployed in production. So there is more to it than just the communication aspect. If we have effective ways of evaluating this model, then we can debug and improve our ML systems. We can explore and discover latent hidden feature interactions, model variability, as we have, once you have operationalized the model, the data set on which you had actually trained the model and the test, and on which the scoring actually happens, there may be a lot of variability in that. What if the feature space changes after you have productionalized the environment, productionalized the model? Helps in model comparison. Data science primarily is an experimental science. You want to experiment with new models, with new ideas, with new mathematical formulations. It could be that a particular model, for example, one person wants to use H2O to build a model, the other person may want to use Scikit-Learn, and there's also a disparity in a lot of the way these algorithms perform across these different frameworks. So having a consistent way to compare these models is also important. Domain knowledge. In old times, there used to be something called as expert systems. Does that ring a bell to anyone? Right? And what was expert system? Expert system will be like, it will give you a UI where you can specify the formulation that you think is needed to actually create that model. You specified, you build a model, that's good. And it will provide you more sophisticated features to that. But over a period of time, as the market has grown and machine learning and data science is the big buzzword, what has happened is that everybody wants to be on board of the ship, which is great. But what is happening is that, I'll give an example myself. Before joining eHarmony, I was working for a startup where I was helping them build analytical models to predict failures in oil and gas industry. And the next day, because it's a practical life reality, I moved job, and then I'm at eHarmony, and I'm trying to evaluate human psychology, understanding how humans are actually behaving. I have no formal background in human psychology, and actually I'm building models to deliver the best matches. Now there's a gap in domain knowledge. And how can we effectively, fasten this process of understanding what the data set is about so that we could build effective models? Consumer. We talked about explanation of a model. It's the same. You go to a business user, the question often is, can you tell me what are the key features which are driving the KPI? Is this possible to check and verify the accountability of a model? Will it be possible to share this explanation, if needed, to the users who are the consumers of this model? Let me give an example. Credit scoring is a common example. So there is actually led by US government in many ways, which regulates a lot of the financial firms, that if we question the credit scoring provider, they have a liability to tell us what features were actually used based on which this particular credit score was delivered. So this is to make sure that no biases are actually committed when this models are built. And the last one is the one we have already articulated, is in identifying and being aware of the failure scenarios. So far we've talked about what and why. So I'm guessing we have some form of an understanding what model interpretation is. Now let's define a scope. So model interpretation could be defined globally and locally. When we produce these models, at the end of the day, we want to understand how is the model doing with respect to the whole data set. You said equilibrium state. Maybe the equilibrium state is 90% accuracy or any threshold that we set. Can we also understand that is global interpretation? Can we also understand how the model is doing for an individual prediction? Like I was mentioning, someone was falsely classified for a particular credit score, and the person queries the financial institution. They have a liability to why the particular prediction was made. And you'll be surprised how many times linear regression models are the ones which are still deployed in production. A lot of experimentation is happening with deep learning models, but I don't have any stats, but I'll not be surprised only 10% of that actually makes it to production. And that's a big problem. And the question is, how can we narrow the gap? So that says, so how do we go about enabling model interpretation? So it could be done in multiple ways. If you have an engineering background, reverse engineering is what we do when we try to fix a problem. A bug occurs, we try to think, oh, how did this occur? What are the use cases in the scenario? So if you think in the same way, post-automation could be one way. So you're building this black box model, you don't know anything about it, but there's some way to put a hook in it and demand an explanation of why, what, and how. Now this could be done in a model agnostic fashion. So there are algorithms like partial dependence plot. Are you guys aware of partial dependence plot? Heard of it? I'll add references to that in the slide. But today we're going to talk about another specific case of interpretable model. Feature importance. We know that, right? We build models all based on these features, and they have some rank order that is being maintained. But rank ordering for these features is not possible for all sorts of models. And I'll explain that in the next couple of slides. Local interpretation. So there is a novel technique which is developed by Rubro and others. And it's a way to interpret models locally. So you can actually ask or demand a single individual prediction to give more information. Deep learning neural networks, there's something called a saliency mask, where, for example, if it's an image use case, it's even more problematic because things are more complex. What if it's a text? So these are more complex scenarios where it becomes much more difficult to actually demand an explanation. So today, we're going to be talking about a probabilistic interpretable model called Bayesian rule list, or alias BRL. It was initially designed by Benjamin Lethem. He's currently working at Facebook. And then further improved by Hongyu Yang. He works with Professor Cynthia Rudin at Duke University, and their primary focus is on how do we build interpretable models. Let me take a pause here. So when we build predictive models, there are there is two paradigms. One is the frequentist approach, that is, you take this black box models and you build it. And one is a Bayesian approach, where you want to sample the whole distribution and understand what you are actually picking up, or which parameters you are actually picking to make these predictive models. So this probabilistic interpretable model is the generative probabilistic classifier. So given a particular condition and the set of features, can I predict whether it's true or false? So it's a classification estimator. It works great for tabular data set. When I say tabular, which means that the feature set is a consistent set of comma-separated CSV file, not CSV file, comma-separated data set, and the feature sets are consistent. It could be sparse, but all rows have consistent set of features. One form of algorithm which falls in this bucket is decision trees. Are we all familiar with decision trees, right? So decision trees are very popular, and then it was superseded by random forest and then SGBoost, is because they could naturally be interpretable. But there is again a problem with random forest. Like single trees are easy to evaluate, but if you increase the depth, then again it's very tiresome and it's not human tractable. Random forest, if you build thousands of trees, how do you go about evaluating a single feature? Are you going to keep track over 1,000 trees, or is there a technique? And so this is a competitor to decision trees, and seems to work pretty good. It's built using pre-mined association rules. So what I mean by that is, say if you have a data set and a set of features, what if you do a pre-compute frequent matching? So you figure out which features are actually occurring most of the time, and then you compute all possible combinations of that. So that's what I mean by pre-mined association rules. Then what we do is we build a Bayesian hierarchical model on these pre-mined rules. I won't get into the details of what exactly is the Bayesian hierarchical model because of the time constraint, but there's enough information so that you guys will then you can go on and read more about it. Once we have done that, typically in Bayesian modeling, what we do is we compute the whole posterior distribution over a particular criteria. Now, in this case, since it's a probabilistic interpretable model, what it does is that it computes a sample from the posterior distribution over the permutation of all possible if and else conditional statements. So this interpretable model is composed of if, then, else conditional statements. Very easy to understand human interpretable model. So that's what it is. It's a logical structure of if and else decision stumps. Scope of interpretation, globally and local. Because if it's an if and else, then even if it's a single prediction, I can understand, oh, if A was less than 50 and B was greater than 60, that's why this decision occurred. So a little more detail. So if you think that we have an IID training example and our feature set is actually encoded because Bayesian rule list algorithm works only for a discrete set of features. So if you have a continuous feature, one needs to convert it. And then, as mentioned, we are primarily looking at supervised learning problems. In this case, binary supervised learning problems. Why this could still be useful? Because more than 50 to 60% of our use cases are still supervised learning problems, and they work really well. So Bayesian rule list. So I mentioned that it's a collection of if and else statements. Each single rule is composed of if X obeys a certain criteria, then this is the probability score, positive probability score. So each rule is independent, and it is selected from the pre-mined rules that I mentioned using frequent matching algorithm. So when we build this machine learning algorithms, any machine learning algorithms, there is one objective that we are trying to optimize it, whether it's a cost function, whether it is something else. In case of interpretable, probabilistic interpretable Bayesian rule list, there are two goals that we are trying to optimize on. One is the accuracy, that is the model scoring function. We're also trying to optimize over the possible set of pre-mined rules and the order to create the final set of interpretable decision stubs. Why we are trying to optimize on this is because mentioned with respect to decision tree, if the number of rules is exponential, then again, it's not human interpretable. So what we're trying to understand is what are the key features with which we can attain maximum coverage in the data set and not lose on accuracy. So this is an example of how a typical output from a rule list model looks like. So you can see, maybe I can take a pause here. And someone from the audience, just looking at this, output, help me articulate what exactly this model is about. Maybe any guesses? Yeah, that's perfect. It's based on a diabetic data set, and truth of the matter is I didn't give you guys any information. I don't have any information what data set it was used, but again, it's naturally interpretable. Yes, true. So I'll mention how we can handle that. But that's the problem with any any model that we build. So this probabilistic interpretable model is a generative model. So what I mean by that is typically in machine learning, there are two primary forms of model. Either it is discriminative model, that is, one can learn the conditional probability of Y, that is the target label that we're trying to predict given the feature set directly. Or we can apply a generative model which computes this conditional probability indirectly using Bayes rule. Are you guys familiar with the Bayes rule? Idea about generative model, what we mean by that? So when I say posterior probability, prior probability, I'm forgetting, likelihood estimation, it rings a bell, right? So we can go through a quick example. So this is a very cliche example, a coin flip example. But in this case, something was wrong with the machine that was minting coin, and there was a bias in predicting head. So irrespective, like number of times irrespective of the number of times you flip the coin, there's a bias that 40% of the time is going to give us head, and the probability that if you flip any number of times that we'll get a head using this bias coin is 30%. Similarly, there is coin 2, which has 60% bias, that is 60% of the flips is going to give head, and probability based on some sample set, it has 70% probability that's going to be head. So now, and we want to understand is that what is the likelihood or likelihood of the probability that if I flip a coin, I'm going to get a head or tail? How do we do that in a generative model? So first, what we do is we compute a likelihood estimation. Then we apply a prior probability. And then using that, we compute a posterior probability. So likelihood estimation is based on something that has happened in the past, what is the probability of occurrence of a particular prediction in future? Prior probability is that from an understanding, from a bias, what information do I have about this data set or this particular use case? Posterior is basically, it's an approximate of likelihood multiplied with prior probability. I've added a reference to a book if you guys want to dig more and understand more as to how these Bayesian rules are made. This is a good book by James Stone on Bayesian rules with Python. So I mentioned that the Bayesian rule list is actually optimizing on the ordering of the rule list that is producing, and also the length as to how descriptive it is. So some errors on the slide. So if you can see here, if you remember, I mentioned that posterior probability, that is the conditional probability of an unknown based on relevant evidence, is actually a multiplication approximately equal to the likelihood into prior. So this D here that I mentioned is actually an ordered subset of rules. And A is, that we see here, is a pre-mined collection of all rules. So what I mean by that is, I mentioned that you have a data set, you pre-computed all possible frequent matches. Now you applied, then you computed all possible combination of this. So if you have A, B, C computed, maybe you want to get all feature combinations of size 2. So you have 4 features, 4 C2, you compute all the possible probabilities for that. Now, the Bayesian rule list objective is to optimize all those possible combination of features and deliver an output which is still accurate and compete with black box models, but give you the output in the most concise way possible. So this is the representation. Digging more into the model representation. So in this generative model, what we apply is a beta binomial distribution. It's a pretty popular way to compute probabilities when we are counting something. In this case, it's a counting case because we have a rule and we are trying to understand how many times did this rule contribute to the prediction. And the beta in this case is the prior in this case is a beta distribution. If you remember the previous slides, I'd shown that we want to produce output as if X obeys a certain criteria, then Y is the probability. So that's what we are trying to optimize on. Cool. So we talked about a brief description of what a probabilistic interpretable model is. Now let's just talk briefly what's the tension between interpretability and model performance. Chris, how are we doing on time? Cool. So let me dig a little deeper into the tension between model performance and interpretability, and why there is a tension between the two. So let's imagine this data set. This is, I took this out of a credit analysis data set. And the x-axis is, say, assume a feature which computes the annual income, and y-axis is late fee amount. And we are trying to predict whether a particular give us good accuracy maintaining interpretability. At this point, so on this slide, what I'm trying to show is, so actually take a step back. So there's a philosopher by the name of William Ockham. How many guys are aware of the Occam's razor philosophy, right? So when everything else being equal, when we are faced with this decision to, when we're faced with this decision to compare hypothetical situations, it's better to go with hypothesis which is making less assumptions, because the probability of it being generic is more. In computational learning, we can articulate it as build models with the objective to produce succinct representation of a training set. What is the way we can summarize the model representation in the most consistent and simplified way possible? So what it did is trying to articulate quantitatively and qualitatively how Bayesian compares to a neural network. So we see that in terms of simplicity, repeatability, and robustness, the model seems to do pretty well. Computation is doing somewhat okay, and scalability is still a problem. So you remember I mentioned about the tension between interpretability and model performance, and it's very difficult to achieve a balance across, in this case, 1, 2, 3, 4, 5, all 5 paradigms. And that's the problem. Like, even if you train a deep learning model, computationally, it may take a lot of time. Scalability may not be an issue, but then interpretability and simplicity and robustness becomes a problem. At this point in time, let me also introduce that the no-freelance theorem. So, as I'm introducing this Bayesian rule, am I also saying that this is the solution to all interpretability problems? So the answer is no. So because there isn't a one-size-fits-all philosophy when you do machine learning models. So it works good for certain use cases, but may fall apart in use cases. But the objective is that having this in an arsenal gives us more confidence that, okay, if the desire is interpretability, maybe I can build an interpretative model. So after studying the algorithm, I decided to do some benchmark, and it seemed to give me good accuracy, good accuracy measured using ACRC for certain use cases. So this one was based on a Titan data set, and as you can see, I trained in random forest, and it is in rulers, and I got somewhat equal performance. Some more benchmarking using the Bayesian rulers. So on the diabetes data set, there seems to be some disparity in the results. But for the Titan data set that I've shown, I'm getting somewhat equal performance. Then I did also with the credit analysis data set, and I've got somewhat similar performance. One is that for all these use cases, the problem type is a supervised classification problem, and I mentioned that earlier. That the data set, the features need to be discrete. So if you have a continuous feature, one has to discretize it. With that, so let me introduce you guys to Skater. And what if you want to get started with, to try and experiment with Bayesian rule right away? We have written a Python wrapper that we have enabled through Skater that you guys can build interpretable models right away. If you like the idea of interpretability in general, do give us stars, and I'm also looking for people who want to collaborate and participate in this path. So how does the API looks like? So we have designed the API in a way that it gives you a natural feel as to you're building any other form of model. So we talked about, I introduced terms like prior and Bayes rule and posterior and stuff. So it may get a little complicated for people who may not have background in statistical modeling. So it becomes easy to give them an idea that you're building a black box model, but actually you're building a Bayesian model by default. So you import a model, you instantiate the class, you call the fit function. This print model will actually print the output as interpretable if and else conditional statements. We provide features or a way to discretize continuous feature space, so you don't have to do that. And then, the usual stuff, you can predict probability scores, you can predict the scores, persist the model if you want to. And since it is learning a lot of, we mentioned that there's a list of permutation and combination of different rules that the model is training on. So if you want to understand more intuition, you can access these rules. So for big data set, how does it perform on big data set? So we have an understanding that it's computationally expensive. What we've done is we do a small trick where we subsample a big data set. So how do we subsample a big data set? Okay. there's a way to subsample a big data set and reduce it to a smaller size on which we can successfully compute an interpretable model. So as we had started this journey with Skater, the idea was to enable interpretability in a very consistent way. Before today, Skater was only about post-hoc model evaluation, but with the addition of Bayesian rule list, now we support interpretability natively as well. So human in the loop is with respect to you being able to hook in and ask questions of why, what, and how to the model as needed. This is an important law that whenever there's an interesting or any unusual behavior in data set, most likely or not, the result of an error is one kind or another. These are the use cases where we have to actually understand how our data set is doing good, like, how is the data set actually behaving. Overall mission with Skater is to add visibility to all sorts of black box model, and Bayesian rule list is just one other form of natively interpretable model. So that's the core objective. There's a lot of future, improvement that needs to be done. I'll share the slides and then open to questions. And like I mentioned, I've added some references here. And yeah, if you like the idea, give us stars. And there's a bunch of open issues. If people want to collaborate and contribute, that would be great. Oh, sure.
Okay. 15 minutes. Yeah, I flew all the way to Sydney, Australia back in October. So I feel I spent $7,000 or whatever it was to get down. So hopefully you didn't travel that far, right? Okay. Thanks, man. That's like similar to your talk on.
Yeah.
Good to see you.
Yeah, that's what I'm trying to do. Okay, done. That's it, right? It's recording.
I have no idea. This isn't my part. Taking. I just go to the chat. Get the link out of the chat.
Which chat? Oh, this is you, right?
It's me. Copy that link, and that'll be. Should do it. There we go. Okay. 1,000, 2, 1,000, 3, 1,000, 4, 1,000. No whammies, no whammies. Big bucks and cool. Okay. Now I'm going to turn on your microphone now that it all works. You good? Present. So it works. Bam. And is it on the Zoom? Everybody can hear me. And Chris, we look good on the Zoom. It's connected. Is it screen sharing? Maybe it's not even screen sharing. I think that. To do this, I guess. Is it screen sharing?
Yes.
Okay. Cool. Thanks, everybody. I know it's late, and I appreciate all the previous talks. Yeah? Good? Yeah? Okay. My talk is a little different, a little less technical, a little more, I'll give you some fun. I want to talk about AI in the real world, and what is AI becoming in the real world now, but also in the future. So let's just think about this question. Try to predict for yourself, where do you think AI will go, and what will it become widespread in the real world in 5 years, 10 years, 30 years, say 50 years? Now I come at it, I should have introduced myself. So I run a consulting firm that helps startups leverage the latest techniques in machine learning, natural language processing, data science, and AI. And it gives me a chance to get to know a whole lot of different people and startups and see what people are trying to do. Everybody wants AI, but the difficulty is finding ways to actually use it in their businesses, right? We're the ones familiar with perhaps the coolest things you can do and all the great data science that you can put to use, if it's only transparent, that is. But translating that into real business applications is a tough task, even if you can explain it clearly. So I think of this spectrum, and I sort of want to introduce this idea that you can think of AI and the types of things that it can do for us along this spectrum, or this dimension. On one side is AI as artificial intelligence, kind of classic AI. And it comes with the fear/belief that AI will replace us, that AI will become so smart, so omnipotent, it will do everything we can do and better, and so we'll become obsolete. On the other side is thinking of AI as augmented intelligence, where its job is to help us do our jobs better, to make us better at what we do. And I'll take you through my thoughts about why it is I think that at the end of the day, AI as augmented intelligence is where we're going to end up in the next 10 years. But let's start with the classic artificial intelligence. Cylons from Battlestar Galactica, the greatest show ever. Replicants, Skynet, the movie Her, where you have this sort of omnipotent, omniscient intelligence in the cloud, to voice of Scarlett Johansson. If anybody's read Ender's Game, the series, there's Jane, there's sort of this AI up in the universe that's kind of watching over everything. So I'll give you a little bit of fun here. Hopefully the audio works.
After that, you can do whatever you want with me.
Does anybody hear this?
Care. Would you mind telling me what's going on? I'm not a fracking Cylon. I'm not. Oh, well. Okay then. Sorry to bust up your day, brother. There's been a change of plans. It's been decided that the occupation of the colonies was an error.
Okay, I'll stop there. Could you guys hear that? Yeah, when you turn up the mic. Thank you. Appreciate it. And then continuing on down this spectrum, getting beyond the sort of classic
fictionalized notion of AI as androids, either human-like beings that are much smarter and better at everything than we are, or something in the cloud. You can think of AI as robots, of course. These are sort of still in physical form. AI is having the ability to do things that we can't do. And the primary way that this is taking hold in actual industry is predominantly through manufacturing, and predominantly in Asia, as you can see from the data here. And this one I think doesn't require much audio, but this is one depiction of a robot that Boston Dynamics has been building. I don't know if you've seen this before. And also take note of the tags that I guess that is the Guardian adds to this. Like, is this scary? Would you be scared by this? So yes, it's terrifying. That's what they describe. So, and if you want to see a terrifying version of that, go watch Black Mirror, the most recent season, the episode about the dogs. So, you know, up there on the side of the spectrum, it's always portrayed as terrifying and scary. It's going to replace us. It's going to kill us off, you know, if we're not careful, kind of thing. Then we get to this sort of middle ground of assistance. And this is becoming much more real world applications. Of course, Siri, Alexa, Google, Cortana, Watson in the business world. I'll play this just for a minute.
Hello, my name is Watson. Welcome to the Karalpa gas plant, operated by Woodside. What you are seeing is a world-class gas production facility located on the northwestern coast of Australia. Working in these challenging conditions, it is important that questions are answered in minutes, not hours, especially for those working on operational sites. That is where I come in. Natural language and conversation APIs allow me to understand many project-related questions, which employees can ask via their tablet or computer.
Okay, I'll stop there. You get the idea. It's all versions of taking advantage of natural language processing, combined with sort of a chat interface, combined with search and other sort of background intelligence in the AI to be able to assist you to do your job. Then we get down to something I'll call process automation, sometimes called robotic process automation. I won't go into it much, but the idea is meant to be take simple tasks that we do every day that can be automated. And the level of intelligence required to do that might not be so sophisticated, but in some cases like contract reading, there was this contest done between 20 real-life lawyers and an AI that was able to read contracts and look for certain entities and keywords and sort of takeaways from the contracts, and the AI kicked the butt of all the lawyers, of course, like 100 times faster and with a higher accuracy rate. So you can look at that as scary for lawyers, like, ooh, the AI is going to replace them all. But you can also look at that as a tool for the lawyers, right? I think many attorneys would tell you that they don't necessarily want to spend all their time on low-level tasks like reading through a contract. They want to spend their time on advising the client at a higher level and using their intelligence and their smarts and their backgrounds and experience to help. So the AI in this case becomes a tool to augment their capabilities, make them faster at their jobs, better at their jobs. We have other things like face recognition, particularly in China, taking hold, where it's doing low-level tasks that you might, in some cases, employ a human to do, or you might not need to. And then at the bottom, I have this broader idea. I'm just calling it human amplification. I was struggling to come up with a term for this, but think further into the future about the ways that an AI combined with the knowledge base that it could develop about us and about a particular domain. So medicine up in the top right, and enhancing the ability of a doctor to understand everything he or she needs to know about you as a patient, and to then be able to do a better job at what she does at helping this patient, by having suggestions, by having analysis and synthesis of information coming in from the AI, and these other situations, farming. I think even just the simple premise of Google Maps is itself pretty amazing, right? That we can drive and not have to know where we're going. We're just told where to go. And then I included Ender's Game in there because, as you can tell, I like it. So I believe that the growth in AI that's going to happen in the real world in the next 10 years is primarily down here at the augmented intelligence level. And I'm not going to have a whole lot of time to build my whole case around why, because I'm going to run out of time pretty soon. But one perspective to take is to look at technology and to look at what AI is able to do right now in order to predict what it's going to be able to accomplish successfully in the next, say, 10 years. So there's all these things that AI and machine learning are able to do really well. But AI is not particularly good yet at understanding us. And as a result, it's tough for AI to predict what's best for us if we're not even sure what's best for ourselves. Having a model and building into a recommender system is a pretty tough problem already. And the recommender systems literature and research is doing a great job at sort of developing ways to predict what you're going to want and giving you the right movie in Netflix or piece of music in Pandora, or even document in Google or many search engines. But this is a tough thing to build into an AI. Holding a real conversation, again, difficult, and NLP is making a lot of progress here to overcome a lot of the challenges of just understanding human language to be able to hold a conversation that perhaps passes the Turing test. Another way of looking at this is to look at what's actually being adopted by consumers. And Alexa is far and away the champion of the first instance of kind of what I call the iPhone moment for AI, where you have a voice-enabled speaker that sits in your kitchen in your living room at all times and listens for a hot word, combined with a pretty decent chatbot. It's not very good, but it's good enough, and the accuracy rate at understanding what you say to it is now gotten good enough that we sort of accept this and see it as this anthropomorphized being. My kids tell me to be nice to Alexa if I yell at her for not understanding everything I say. And I think this type of voice assistant is here to stay. And I'll finish, because I want to respect everybody's time, on the idea of looking at it from an economics perspective to say, despite the desires of whatever it is that we in Silicon Valley and technology want to deliver to the world and often dream about, one way or another, replacing people. I spent a lot of time in the fintech payments industry, and the dream is to basically replace waiters and waitresses and all sorts of service workers, so that instead of them having to service you to give you a coffee and take your credit card, we can just go like this and tap, and it's all done. Or maybe not even do that. But that doesn't happen, because I think that in truth, there's a kind of there's a way that we build economies around labor, around service labor, and there's skill sets inherent to every job, even low-level jobs, and technology does not tend to leapfrog that and just skip the process of becoming a tool for employees and just all of a sudden put them all out of work. And you could go back in the history of automotives and the internet and telecom, and again and again and again, it's never a process of simply leapfrogging and displacing massive parts of the labor force. So here the slide's talking about the ways that business executives are actually trying to put AI to use. And I think that also, from an economics perspective, the cost of robots is going to be higher, much higher than human labor costs for a long time. And I think we're a long way from AI or robots being able to replace skilled labor. And I'll skip past that and just say, I would personally prefer to focus on the ways that AI is going to enhance us and make us smarter and make us, better at doing our jobs. And I think that that's the way that AI is actually going to become prevalent, at least in the next decade. So that's it. Thank you, guys.
It's 9:02.
All right.
Thanks for me. Thanks, Brett. Thank you. Thanks, Andrew.
Thank you. I'll let you.
Thank you.
Thank you. Thanks
I'm
for
glad to hear that you're